thank you for inviting me to come speak about these projects. It's a pleasure to be here, as always, in Bonn. It's going to take me a moment to get used to this earpiece. I really feel like I should be trying to convince you to buy a new iPhone. And if you've seen me talk about this before, I hope that you brought something to do, because you're going to look like a jerk if you get up and walk out now. But yeah, so this is a joint project with Dustin Clausen, Mathew, and Nico Naumann, some fantastic collaborators. We've had a lot going on for a while now. Yeah, as the title says, I'm going to talk to you about Galois descent and Redshift and algebraic K-theory. So this is an algebraic K-theory conference or workshop. I'm going to give you a bit of a background on chromatic homotopy theory, which maybe many of you are not as familiar with. It's a bit difficult to, you have to be well organized to explain chromatic homotopy theory in one seminar course. So it can take quite a while, but it turns out to be quite a bit easier to do it in a few minutes. So first let me talk about sort of periodicity phenomena in stable homotopy theory. So here we have, for every prime p, there's a self-map of the sphere spectrum. So maybe you're not so happy with that. You could think of this as the K-theory of finite sets, if you like. And then this map is given by, say, taking a finite set and crossing with a fixed set of order p. So we have the self-map, and what we know about it, well, it induces an isomorphism in rational homology. Rational homology is awesome, very easy to work with in spectra. In particular, you could just get it by taking homotopy groups and tensoring them with Q. For this talk, we're going to call rational homology K0. You'll see why in a second. So if I take the cofiber of this map, I get a spectrum called S mod P, which you can use to, say, construct K-theory with Z mod P coefficients. And what do we know about this one? Well, this also has a self-map, which I call W1. And this map induces an isomorphism in another homology theory called K1, which can be constructed by taking this E1 theory and quotienting by P. Well, what's E1? E1 is topological complex K-theory, completed at a prime P. So why do I care about these things? Well, one of the things I get out of this is that the fact that these two maps induce isomorphisms in some homology theory means that, well, if I take a large power of those maps, they also induce an isomorphism in those homology theories. In particular, the maps are never null. So they're non-nilpotent. So you can construct sort of periodic operations, or you get sort of periodicity in the homotopy. Great. So Davenant, Hopkins, and Smith have a beautiful result about ways to detect these sort of periodic phenomena. So if I set F0 to be the sphere, F1 to be this cofiber, then you can probably guess from the notation, I can inductively define some Fn plus 1 by taking Fn, quotienting by a self-map Wn. And what's amazing is this, we can get these self-maps so that they induce an isomorphism in some other generalized homology theories. These are called Morava K-theories. And they can again be constructed by taking some homology theory En and quotienting out by some maximal ideal. These En play a real central role in chromatic homotopy theory. They have all the sort of structure you want, and you want to reduce problems to understanding them with En. So we can think about these Ens with their maximal ideals as some sort of higher analog of topological K-theory. So by construction, these finite complexes have trivial n minus first Morava K-theory, because I quotient out by some map that had an isomorphism. And they can set it up so that the nth Morava K-theory of this guy is non-zero. So when you have a finite complex with these two properties, we call it a type n complex. Okay? So it's just a name, but it's nice that n and n are the same here. Right, so the results of Davenant, Hopkins, and Smith are really about the periodicity in these endomorphism rings. I think we can always construct these sort of self-maps. All right. So one of the main results is this nilpotence theorem. So if I have some sort of algebra in spectra, or like an A-infinity algebra, I have some element in its homotopy, then of course there's an easy equivalent here. This element is nilpotent if and only if the ring spectrum I get by inverting this element is contractible, or zero ring. So we can restate everything in terms of this. So if I have some algebra in spectra, this guy is contractible if and only if for every prime p, the fp homology of R is 0, and all of these Morava K theories vanish on R. This is a beautiful result, and you can think about this as giving you a way to detect all these sort of periodic maps. Very tractable condition. It sort of lets us organize all periodicity phenomena by looking at these different ends. So, right, so any periodic map should somehow be detected in one of these homology theories. So the name Redshift from the title comes from the fact that these KNs detect self-maps of degree divisible by 2 to the p to the n minus 1. So they induce sort of periodic patterns of longer and longer links as n grows. So you guys think about this sort of period gets longer, so it's sort of a, if you're thinking about a chromatic analogy here, these sort of more and more red waves, like sort of going off. All right. So in the 80s, 86 I think, Peter May made a conjecture which is supposed to sort of simplify this result under some stronger hypothesis. So the result is now, rather than just having an algebra in spectra, I take a commutative algebra in spectra. So these are also known as E-infinity ring spectra. And the result now is that a ring here, an E-infinity ring spectrum is contractible if and only if its integral homology is 0. Now this is very nice, sort of one sort of elementary algebraic homology theory can be used to detect this periodicity, these periodicity phenomena. This was proven first by Mike Hopkins, and he didn't publish it or let anyone else know about it, but Akil, Mathew, Nico, Naumann, and myself, we proved and wrote this up in 2015. So I don't know how Mike exactly did it, but I can tell you how we did it. So the proof of this conjecture is really just two parts. One, a very, very hard part, the Devenant-Hopkins-Smith nilpotence theorem, and a very key lemma. So this shows that if I have a commutative algebra in spectra, then all of these Morava K theories vanish, precisely if just the rational homology vanishes. And this is, as you can imagine, is a very useful result. So in particular, you could see that this is 0, which is just tensoring this ring with Q, if and only if pi naught of R tensored with Q is 0. So if pi naught is torsion, then all of these things vanish. It really tells you that torsion phenomena are somehow very algebraic in E-infinity ring spectra. I should also point out that this is K0 of R. There's Jeremy Hahn recently proved a generalization of this result that showed that if Kn of R vanishes under the same hypotheses, then all the higher Morava K theories vanish. That's a beautiful generalization and much harder to prove. It's impressive. So the general theme of this talk will be to reduce hard questions in chromatic homotopy theory to easy questions about pi naught tensor Q. And somehow look at a given problem, try to find the obstruction to something being an equivalence, and show, oh wait, this obstruction is really a module over the 0 ring, and so I'm done, the obstruction will vanish. So if that was all hard for you, then this is an easy slide to take us back. So algebraic K theory, right? This is a functor from rings to spectra. I'm looking at the connective version, but everything will work for non-connective spectra as well. What's important is that if I take in a commutative ring, what I get out is not just any spectrum, it's an E infinity ring spectrum. So I can tie in to the results I was using before. And of course, this is something everyone here knows, that I can understand these K-naught groups as this sort of Grothendieck group of isomorphism classes of finitely generated projective R modules, where we get this sort of relation from short exact sequences. And this will show up later when I want to look at more involved input for K-theory. I want to use this very elementary relation quite often. And of course, we can extend these things, K-theory, to exact categories, schemes, stable, idempotent, complete, small infinity categories, and Waldhausen categories. Right, so now I'm going to remind you about Lichtenbaum-Quillen or Quillen-Lichtenbaum conjectures. So you can, the stated version is from this ICM address of Quillen in 1974. So he says that one might hope to have some spectral sequence analogous to the Satia-Herzberg spectral sequence in topological K-theory. So this should be some sort of spectral sequence going from the ordinary cohomology, which in this case is some Étale cohomology, to the algebraic K groups after completion. And he said that this should converge when these groups are sufficiently high, very concrete bound. So Thomason and Thomason's spiritual accompaniment prove some a result along these lines. So they suppose that if we have some Noetherian ring with finite Kroll dimension, L is a unit, and a bunch of other technical hypotheses, then there is some spectral sequence, and they can identify what it converges to. It converges to some sort of localization or completion of the algebraic K groups. So you can really compare these two things and try to say, okay, now we know what we're getting. Maybe we want to try to relate these two. So what is this guy, this K1? Well, that K1 is the K1 from earlier. So let me tell you a little bit about Gauss field localization. So if I have two spectra, Y and E, I could say that Y is E local if for every spectrum with trivial E homology, the spectrum of maps from X to Y is the zero spectrum, contractible. So informally, you could say that the E local spectra are blind to the objects that E can't see. So it's some sort of simplification. So Gauss field showed that given any spectrum E and any such X, there's always a map from X to some guy LE of X, such that this map is an E star isomorphism, and LEX is E local. So we have this localization functor. And just these properties tell you that it satisfies a universal property here. So one of the localizations we might want to think about is something LN localization, which can be shown to be equivalent to a localization with respect to each of these K theories. This is at the heart of modern chromatic homotopy theory. We try to look at, like, say, the stable homotopy groups of spheres, and we just go blind. There's just too much information. It's too hard to see. So what we do is we put on our KN local or LN local glasses, and we cut out almost all of the information and look at a much simpler picture. And we gradually try to understand more and more of the structure as we allow more and more coarse sort of or more refined localizations. Okay. So returning back to these Quillen-Lichtenbaum conjectures, we can now sort of rephrase the problem. We have a localization map from the LI completion to this K1 localization, and the conjecture is really that the fiber of this map is co-connective, and we can understand it's bounded above, and the top group is given by this dimension of A, +1, I guess. If you just knew that result, you could get something kind of remarkable, which Michels proved in 1990 by different methods, that these Kn localizations of the algebraic K-theory of A vanish for all n greater or equal to 2. This is because Morava K-theories for n greater or equal to 1, they don't see co-connective things. Those are somehow too algebraic. They're all 0. So if you apply one of these localizations, then this becomes an equivalence, and this guy ends up, in fact, being 0. So it's kind of an interesting result. It says that if we try to do this chromatic homotopy theory picture, we don't have to do infinitely many n. We actually just have to do sort of K0 and K1 to get the best approximation chromatic homotopy theory can give us. And so for discrete rings, the Kn localization is 0 when n is greater or equal to 1. And once we apply algebraic K-theory, we get that it's 0 for n greater or equal to 2. It turns out that the K1 localization is usually not 0, as this spectral sequence will show you. So what you're seeing is some sort of shift. Something that's sort of chromatically concentrated in height 0 goes to something that's chromatically concentrated in height 0 and 1. This is this redshift phenomena we're trying to understand. Redshift. So in comes so-called brave new rings, as Waldhausen called them. So he predicted that the K-theory functor extends not just from rings to spectra, but to say, you could pass through A infinity algebras or ring spectra going to spectra. Or you could take, instead of commutative rings, you could take E infinity rings and get commutative E infinity ring spectra. Moreover, we know that we can recover, say, the p-local sphere from this inverse limit of these localizations. And Waldhausen was very interested in trying to understand the K-theory of spaces, this A of a point, which Carey was telling us about, which is some K-theory of this sphere spectrum. And we get a map here. And so Waldhausen was sort of advocating trying to use this chromatic filtration to try to understand this guy, even though we actually know basically nothing about how far this map is from being an equivalence. So we now need tools for calculating the K-theory of ring spectra, something like this Lipton type spectral sequence. So turns out Thomason's descent result reduces to Galois descent. So really, if you prove an Isnavich descent and the sort of Galois descent, and you'll end up recovering a Tal descent. So what is Galois descent telling me? So we're not going to worry about sort of pro-groups or hyper descent. We'll just deal with ordinary descent for now. So G is a finite group. That's sort of key. So we take a finite Galois extension of field satisfying all these hypotheses that Thomason threw at us. Then there's an induced map from the algebraic K-theory of A to the algebraic K-theory of B. And this guy has a G action. And so it lands the homotopy fixed points here. And basically the descent problem in this case is how far is that from being an equivalence? And he proved that it's an equivalence after doing this K1 localization. He also proved it's an equivalence after K0 localization. So this is a nice result, and we try to take a look at how he does this, because we're looking for something like this in ring spectra. For that, I need some notion of a Galois extension of ring spectra. And Rognes developed a very beautiful theory. So you take some E-infinity ring spectrum A, commutative algebra, and a commutative B, A algebra B, equipped with a G action. Again, G was always finite. We're only going to do finite things. So then we say that this is a G Galois extension if the induced map to the homotopy fixed points is an equivalence, and if I sort of restrict to A modules and induce back up, then I get a B module with a G action, and it should be equivalent to this guy, this co-induced G module. And this generalizes the classical picture even for commutative rings. There's also a KN local analog, which he focused where we do we can look at KN local algebras and then ask this to be an equivalence in the KN local setting. So Ausoni and Rognes made a Galois descent conjecture motivated by what we already know for commutative rings. So to set this up, we take one of these finite type n+1 complexes from the beginning, which has this endomorphism V, self-map V. And we form what's called a telescope. We take this finite complex and we invert this endomorphism. So the conjecture from 2008 was if you have a KN local Galois extension, G Galois extension, then they get an equivalence from K of A to the homotopy fixed points after you smash with T. Another way to say is it's a T local equivalence. If you notice, these parentheses don't resolve any ambiguity. So it's a sort of clever typo. So it's very subtle as to whether or not you want to smash with T and then take homotopy fixed points, or take homotopy fixed points and then smash with T. So you can interpret this as saying they're not going to take a stance as to which one they want. Or maybe they mean both. So an important thing to know is that if I had this sort of T equivalence, then this implies that it's also a Kn+1 equivalence. So that is, I'll have a map from K of A to the homotopy fixed points on K of B, and that's a Kn local equivalence. They also formulated an analog of the Quillen-Lichtenbaum conjectures. So to match their notation, we'll call this Fn+1V. And they made the following conjecture. So we have a suitably finite Kn local commutative S algebra. So they say, for example, this could be a Galois extension of the sphere. Then the map from V/K of B to this telescope induces an isomorphism on homotopy groups in sufficiently high degrees. In other words, the fiber is co-connective. And for the same argument I said before for Michels' theorem, this tells me that if I do a localization, a telescopic or Km local telescopation for a bigger one, then in fact these will all be 0. So somehow we're getting this sort of predicted shift phenomenon. You'll get something who has trivial Kn+1 homology, this B. Apply K theory and you'll get something which has trivial Kn+2 and higher K theory, Morava K theory. All right, so that's just the part of this big picture. This K theory should increase the bound on the chromatic complexity. There should be, there's a lot more data to this, but this is the part that I can actually say something about. It's really it's an impressive and bold conjecture. So what evidence do they have for making these conjectures? So if they have a Galois extension of, say, characteristic 0 fields, and A satisfies Thomason's conditions, then this Galois descent conjecture is just a special case of Thomason's theorem. There's a CP-1 Galois extension on KUP. So KUP has an action by the p-adic units, and this sits as a finite subgroup in there. And if you look at the homotopy fixed points, you get some spectrum LP, and this is a Galois extension. And so they checked that, in fact, you do get Galois descent here. You should note that that's not a lot of evidence for the higher conjecture. This is very restricted, very nice case. So for the sort of Quillen-Lichtenbaum type conjecture, if I have a field of characteristic 0, again satisfying Thomason's conditions, then the Rosvovodsky proof of the Bloch-Kato conjecture, as explained by Levine, actually implies this Quillen-Lichtenbaum, which is the same as the Ausoni and Rognes Quillen-Lichtenbaum conjecture for B. All right. And they also have some calculations for primes greater or equal to 5, this set of spectra here, these Galois extensions and their connective covers. They were able to calculate both sides and show this conjecture holds, the Lichtenbaum conjecture for B. So this is very hard. It's a lot of work to calculate both sides. Again, it's not a huge amount of evidence, and these are really some of the easiest things people study in chromatic homotopy theory. So it was really quite bold and a nice insight to try to make this conjecture, or these two conjectures. Right, so what can we say about these conjectures? We proved it last year. If I have a map from A to B to be one of the following finite G Galois extensions, so for example, any Galois extension of fields, we could drop all of the hypotheses that Thomason puts in. You don't have to worry about units. It's not really a result about being away from the characteristic or anything like that. If I take the C2 Galois extension from topological real K-theory to complex K-theory, where you just complexify vector bundles, or sort of analogs of these for these Lubin-Tate theories, if I take any finite subgroup of this extended Morava stabilizer group, as shown by Leonard Meyer, Nico Naumann, and myself, this gives a Galois extension that will satisfy our conditions. Any Galois extension of sort of TMF with n inverted, any G Galois extension of TMF0n, so this level structure version, then the induced maps here from K of IA to K of B's homotopy fixed points to the homotopy fixed points after this localization, their equivalences for any periodic localization. So what exactly does that mean? So that means like any of these localization functors, T of n, K of n, something that's built from a wedge of these T of n's, something that's built from a wedge of these K of n's. Both of these maps are equivalences, so it doesn't really matter how you parenthesize. So it was a good conjecture. So what else do we get from these sort of descenting? So again, when A to B is in the LTs as above, then there's an associated spectral sequence and an analog of the Sital to K-theory spectral sequence, which goes from the group cohomology, acting on these homotopy groups, to the homotopy groups of the base ring. And what's remarkable is that these spectral sequences always collapse at a finite stage. You don't have to keep chugging along. Moreover, if S is large enough, the groups will be 0 there. So there's really a finite sort of horizontal vanishing line, which means, for example, your extension problems are finite. So it converges very rapidly. We also have descent results that are not of Galois type. So if I have a map of rings from A to B, say that's faithfully flat, finite, and say pi star B is a projective pi star A module, then we also will have a descent result, sort of a tote tower. So we get sort of local flat descent. So also for these connective covers of KL and KU, you get a descent result there. And for TMF, one with 3 inverted, passing to its level structure version, we will get these sort of descent results. Also, we didn't really need to take connective algebraic K-theory. I could take its non-connective form. I could take THH, TC, any sort of localizing type invariant. Great. Any questions? Good. So we can't quite get to the Ausoni and Rognes Lipton conjecture, but we can prove some of these vanishing results that are predicted by Redshift. So we also give a new proof of Michels' theorem. So if you have any, not just a ring, but say a ring spectrum over HZ, then the Kn homology of K of R is 0 for all n greater or equal to 2 and all the implicit primes inside of this guy. That's just Michels' theorem, but we have a different argument. But the new argument also extends for doing things like Kn star of K of Ku is 0 for all n greater or equal to 3. And the argument I'll talk about today works for the primes 2, 3, and 5. So if you combine this with the work of Ausoni for primes greater or equal to 5, we can now say this is true for all primes. We actually have a lot more examples of this type now, in particular at the prime 2. So you can use Galois descent and localization sequences to say the same sort of vanishing results hold for real K-theory and these connective covers. So how do we prove this Galois descent? Let's do the easy case, which is the easy case of Thomason's descent result. So he showed that Galois descent rationally for fields is really quite easy. So if you have a G-Galois extension of fields, there's a transfer map, which we heard about, going from B to A, which is rationally surjective. So the class given by B forgets to a free A module indexed by G generators. So you pass this guy, and this guy is just Z. So rationally, this hits a multiple of the unit. Now, Thomason then uses a very nice transfer argument, which I'll talk about in a minute, which shows that from this you can show that these maps are all equivalences, no matter how we parenthesize it with these rationalizations. What's fun about this is you can trace through some diagrams relating these K of A, which is sort of like the genuine fixed points, to the homotopy fixed points. And you can show that if you have both of these equivalences, then you get that this map is rationally surjective, which is where we started. So these two equivalences are equivalent to this condition. So we know where to look. In particular, any descent result that goes up to higher heights should satisfy this sort of condition. So how does Thomason's transfer argument go? So we have our Galois extension as before. Mona Merling and Clark Barwick and his big clan have this beautiful way of constructing algebraic K-theory of this Galois extension I mean, as a genuine G spectrum, this was already sort of done, but in fact, it gives me an E infinity algebra in genuine G spectra. Not E infinity, if you know a lot about these things, this is not the sort of E infinity with norms, although it's probably true with norms. This is just sort of ordinary E infinity. So this genuine G spectrum has the property that, so it's G fixed points, gives me back K of A. And if I take the underlying spectrum, or the fixed points of the trivial subgroup, I get back B. So what we really want to do is compare the G fixed points to these homotopy fixed points. And that comes from looking at a certain map. So we go from K of A to K of B, homotopy fixed points. And we very explicitly understand the fiber. So some sort of mapping spectrum from this guy, E twiddle of G. This is a G space, a pointed G space. Its G fixed points are S naught. And on all the other subgroups, it's contractible. So we have that guy. So really, this is the error. This is the problem we want to get rid of. So we want to show that this, actually, if we localize K of A with respect to all these things in K of B, then we want to show that this sort of, you'll end up seeing that this guy is in fact, this guy is always a module over this. And if I do the localization in either place, this thing is always a module over the ln, the suitable localization of this guy. So this is a nice ring spectrum. So Thomason's case is just n equals 0. All right, so what we need to show is that this guy is 0, and then this guy will be a module over the 0 ring, right? Right, so how do we get at this guy? Well, we have a fiber sequence where we take the homotopy orbits, and it maps on B going to K of A, and then there's a cofiber. This is, again, we just explicitly understand it as this guy, the ring that controls the trouble. And there's another map, K of B, you could pass to this homotopy orbits. And this composite from here is the transfer, again, like from Carey's talk. We want to show this localization of R is 0. We had an assumption, and our assumption was that this guy is rationally surjective. So this composite is rationally surjective. So we had a multiple of the unit under this map, or rationally had a multiple of the unit. And that tells me that pi naught of R here will be torsion. So as I rationalize it, this becomes 0. And that's great. So that tells me the ring is rationally 0. And the argument I just sketched out tells me this proves Thomason's rational descent. Then we have the new input. We have May's conjecture now. That shows me that all these localizations are 0. And that proves all the Galois descent. So it's really a very powerful tool. It comes in just to, takes a classical easy argument, and we produce this much more general descent result. Okay. So, to summarize this argument, when I have a G Galois extension, then these induced maps that we want to see are equivalences. They're equivalences for any localization if and only if this map is rationally surjective. And that's the condition you have to check for each example we go through. Unfortunately, it's not like just one argument that we seem to be able to apply everywhere. You really have to do some calculation in k naught of these two things. And these are still pretty mysterious objects. So, like, how does one do this in one of these new contexts? Let's check this condition. So, our real most interesting elementary case here is this C2 Galois extension from K-theory, topological K-theory. What we want to show is that the class of Ku forgets down, so by this transfer map, is a multiple of the unit, which is the class of Ko. In fact, it's 2 times that class. So how do you do that? So this would give me the rational surjectivity we need, and would then imply the Galois descent results we're looking for. So the argument is as follows. So a result of Wood shows that there's a map eta, a degree 1 map, which comes from non-trivial generator in pi 1 of Ko. And the cofiber of that map is Ku. So that's really the theorem to check, is that this cofiber is Ku. So you just extend that exact triangle over, and you'll get the double suspension here. And I look at this guy, this little short exact sequence. And what does this give me in K-theory? It says the middle thing is the sum of these two guys. So Ku is the sum of these two. And you play with the things again, and you could see that the suspension of a class is equal to minus the original class. So if you double suspend, you get back the original class. And now that's Ku is Ko plus Ko equals 2Ko. And that gives us our descent result there. Right, so what about these bounded chromatic complexity theorems? So this is a very indirect argument. So we take a commutative algebra in spectra, and we take this elementary abelian P group of order P to the n. And I look at the group cohomology, the E-valued group cohomology of this guy. There are, again, sort of transfer maps from proper subgroups. Here we look at the subgroups of order P to the n minus 1. And they go over. And my condition is that this map is surjective. So we get a rational surjection again on some other transfer. What does that tell me? That tells me that all of these Morava K theories vanish for Kn plus K for all K greater or equal to 0. Sort of bizarre result, I think. And it's part of a general picture relating equivariant homotopy theory and chromatic homotopy theory. Here's a sketch of this proof. So I want to show that Kn plus K smash E is 0. Well, that's true if and only if I smash with one of these Lubin-Tate theories and smash with E, and then I do this localization and get 0. There's an augmentation map, and in fact, so you get this implication is very easy. The other one requires a bit more knowledge. Now, to show that this guy is 0, by the May conjecture, I just have to show pi naught of this guy is rationally 0. How do I get at that? Well, if I look at this is somehow, again, we reduce problems to Lubin-Tate theory. So this guy is much easier to understand object. So when I look at the R cohomology of BCP to the M, this abelian group, it's always a free module over this point. And I can actually count the rank. Now I get a map from E to R, so I'll get a commutative diagram of transfer maps. And the rational surjectivity over here will imply the rational surjectivity for the diagram where E has been replaced by R. But now I have a surjection between two free modules, and I can just calculate the ranks. And what you see is that this side has larger rank than this side. So the only way that I could get a surjective map between two free modules over a commutative ring where the target has larger rank is if the ring's the zero ring. So that tells me this guy is 0. And then we can just go back, and we get back to this vanishing result. So I have to check this condition. And the cases I've been telling you about is when E is the algebraic K-theory of something. I mean, we work really hard to calculate the algebraic K-theory, that cohomology theory of a point. Doing it for these BG and BA, that's going to be tough. So how are we going to get at it? We're going to cheat. So instead, what we're going to think about is G representations in R modules. So R modules with a G action, which are non-equivariantly compact. So if you're used to this language, this is the K-theory of fun BG to perf R. And it really is a generalization of representations, K-theory. So there's an analog of this Atiyah-Siegel completion map, which goes from the H representations of R modules to this group cohomology. It's also just an analog of the homotopy fixed point map I was talking about before. So using this map, we can show that if we get the rational surjectivity for this representation K-theory, I again get the rational surjectivity for this group cohomology. So now we have to check an induction theorem on representations in R modules. So we can only do this in some special cases, but let's, for example, if we take the integers and we look at H representations, we take the cyclic elementary abelian group of P group of order P squared, then we get a surjection involving these proper subgroups for every prime. So this isn't new. This was due to Swan. This is a classical result. A new one is that if you do this for KU module, just with an H action, and we do this elementary abelian P group of rank 3, we get a surjection for these primes, 2, 3, and 5. So, as we already argued, this implies these sort of vanishing results. And it'll also imply vanishing for any module over the K-theory of Z or the K-theory of KU. You could combine this with Galois descent to go back to sort of subrings under sort of Galois extensions. So how do we do, say, Michels' theorem? So I can look at the regular representation of CP, or sort of the sum of the non-trivial characters. These define two group homomorphisms from CP to UP. They don't commute, but the commutator hits a scalar. So it defines a projective representation of the CP cross CP. That guy naturally acts on complex projective space, P minus 1. And this is totally explicit. You can now look at the fixed points of this. And you can see that there's no fixed points. Nothing is fixed by the entire group. You always get isotropy in proper subgroups. So what does that mean? That if I look at this CPP minus 1, I induce it up, so I smash with HZ. This is now a representation of Z, so it's a chain complex sort of representation of this group. And if I just filter it by its cells, the equivariant cells, it's built out of induced cells. So that's in the image of this induction map I want to study. What I now want to know is that this hits some non-trivial multiple of the unit. There's another filtration you can use. It's a Postkov filtration, which is really just like looking at the homology groups of this guy. This is a Z, and degree 0, 2, up to 2p minus 2. And those will have actions by this group. Because they factor over a connective group, the action's trivial. So that Postnikov filtration, and sort of like just short Devisage type argument, it tells you that in fact you're getting p copies of the unit. So this induction map is rationally surjective, and that proves Michels' theorem. So sorry about skipping through that. Now for k of ku, I'll do something a little bit more fancy. So here's a result of Armand Borel, 1960. Shows that there's an embedding of Cp cubed into the exceptional Lie group E8 that does not land inside of the maximal torus, if and only if the prime is 2, 3, or 5. It's a crazy result. A crazy result. What does that mean? Well, it means if I take this flag variety, it's E8 mod the torus, I get an action on here. Because the action didn't land in the torus, it doesn't have any Cp cubed fixed points. The isotropy is always proper. So if I look at the associated K-theory class, this representation K-theory, it's again in this image of this induction map. So a theorem proved in a different paper, again by Akil and Nico Naumann and myself, we proved that there's an equivariant equivalence between Ku smosh E8 mod the torus and 696,729,600 copies of Ku. So this is the order of the Weil group. And it's not too crazy to see that they have the same rank. Where it's harder is to see that this is an equivariant equivalence. I didn't really say what I mean here because it's true for about any meaning you want. So the result actually shows by looking at genuine E8 equivariant Ku and studying the category of modules over that guy. Now, that's a complicated category. Equivalences, you have to check an equivariant map is equivalence if it's an equivalence on fixed points for every closed subgroup of E8. There's more than a few of those. But what we show is that, in fact, it suffices to just check fixed equivalences on the E8 fixed points. As the category of modules over Ku sub E8 is equivalent to modules in spectra over the fixed point spectrum. And then we can actually just use this calculation. Oh, it's it's a free module. And then get a nice result that's actually an E8 equivalence, an equivariant, genuine equivalence. And then I can just restrict to any subgroup I like. It's still an equivariant equivalence. So this is in particular not zero. So the map is rationally surjective. And we get the vanishing result for K of Ku. So there are some other new results. So these may be of less interest to the algebraic K-theorists which fill this room. But these are all at the prime 2. But they involve higher heights, which I consider very strong evidence for these sort of redshift conjectures. So an easy argument says that MO, so this is some Bordism spectrum corresponding to unoriented real Bordism of manifolds, says the homotopy groups form that Bordism ring. And that, in fact, is the graded homotopy groups are in F2 algebra. So the first and higher Morava K theories of this guy vanish. That's not so hard. You don't need anything fancy for that. Of course, but our argument does in fact show this one, which is due to Quillen. If I do oriented manifolds, then k2 plus I star if this thing vanishes. So this again gives me a result of Quillen's type, but only at the prime 2. Spin manifolds, we get k3 plus I if this guy is 0. This tells me these k groups vanish for ko. So these implications are always there's actually a map of rings going from this guy to this guy. Sort of orientation. M string. So string manifolds, you have 4 plus I star 0. So k4 plus I star of k of TMF is 0. And this keeps going. You can form, these Bordism theorems are all constructed by taking connective covers of BO and forming a Thom spectrum. And if you know what the expected sort of chromatic complexity of this guy is, then you're getting exactly the redshift you would expect here. But we don't know what those map to. It's not really clear. So the proof is sort of easy here. So if I take C2, this cosmic space, so that's RP infinity, I could smash it together L times. This is just BO1, smashed together L times. So I could, each of those maps into BO, but these guys are connected. So as you smash together these connected guys, you get more and more connected source, and it lifts to a higher connected target. So if you look at what this is classifying sort of a virtual representation of this group. If you take C2 mapping down from the Cartesian product over. It's just take the reduced sign representations and tensor them all together. So this guy V, if I take its 1-point compactification, inside of here is a S minus 1. If you look at the fixed points under this whole group, these guys are not fixed. So you're just getting this minus 1 part tensored together. So you get a cofiber sequence. This cofiber is now has proper isotropy because I've collapsed out the fixed part. So if I look at the associated representation class of X, well, it's equal to this guy, plus the cofiber, which is minus this one. And it's in this image of this induction map. And it's oriented by construction for this MO. It has this lift, which means that this SV becomes a trivial representation. And so this becomes the unit. This becomes minus the unit. And again, 1 plus 1 is 2. A somewhat longer argument shows a different result, which I can't prove here, but I can state. So again, at the prime 2, and we take G as some finite subgroup of the extended Morava stabilizer group. Then maybe G is not good because I've been using that up here. This guy has m plus I star equal to 0 for I greater or equal to 2. So this is really, at the prime 2, we seem to have pretty much the set of results I'm looking for as evidence for this red shift. And again, the same reason the prime 2 appears is the same one here. All of these arguments involve being clever about constructing representations. And here, sign representations are sufficiently clever. So you can calculate what's happening over here. It's just a bit more involved argument in this case. But the essential part is just do it for En and use Galois descent. All right, so thanks.